morning, everyone. It's my pleasure to give a talk to share some of my research experience in our department retreat. Today, I'm going to talk about semiconductor core-shell nanoheterostructures. So there have been a lot of applications using semiconductor core-shell nanoheterostructure. People have used this kind of material to make light-emitting diode, lasing material, photodetector, and even television. And this kind of material is highly emissive, so it is also used in bioimaging, although the toxicity is still a major concern. And another property about the semiconductor core-shell heterostructure is this kind of material has strong absorption in visible light range and highly photo-bleaching resistance. So it is also considered to be a great potential candidate in photovoltaic applications. And in terms of energetic, we can simply have two kinds of heterostructure. They are type 1 and type 2. So it's actually based on the conduction and valence band alignment of two different materials. If the band edge alignment is in a closed form like this, it is type 1. And when you have the band edge alignment, which is staggered like this, and it is a type 2 material. And in my research project, I mainly focus on type 2 material. So why I want to study type 2 material, it is because there is a highly desirable property which is charge separation. So upon photoexcitation, we create electrons and holes pairs inside heterostructures. And these two materials, the electron and hole are separated into two domains, here and here. Electron in one material and the hole sitting inside the other one. In such kind of configuration, the charge separation state has a long-lived lifetime. So, as it has a long-lived lifetime, so we have it's has a pretty good property we want to use in photocatalytic and photovoltaic device. And since this kind of material, the electrons and holes inside this kind of material experience large quantum confinement effect. So it is also known as quantum dot. Actually, the term quantum dot is even more well known. And in terms of morphology, they could be nanoparticles, nanorods, tetrahedral, or even more complicated structure like this. So how do we get this kind of nanoparticles? Here shows a typical setup in our group. So we have a shrink line equipped with, we have a reflux system equipped with shrink line. By adjusting the amount of precursors, ligands, reaction temperature, and duration, we are able to make this kind of tiny nanoparticles. And here I want to give you an overview of my study. So the system I choose is a series of core-shell particles. And these core-shell particles has a constant cadmium telluride core and the increasing cadmium selenide shell. And we want to study when we change the shell coverage, how does it affect electron and hole transfer through the interface? Does the shell coverage affect the electron and hole relaxation? And also we want to know, is there any change of the quantum yields and the surface passivation as I deposit the cadmium selenide shell on it? So here is the core-shell quantum dot. So they are colorful under UV light excitation. So we are able to make the quantum dot which covers the visible light range. And in this figure, I have the UV absorption and photoluminescence spectra shown in solid and dashed lines respectively. So here I want to point out several things. So the first one is just the cadmium telluride core. As I deposit the cadmium selenide shell, you can see the absorption red shift as well as the emission spectra. And the red shift is due to the reduction of the quantum confinement effect. And as I deposit the shell on it, you can see this band, which is labeled by diamonds. This band becomes more prominent. As I deposit the shell, this band becomes stronger, and we assign this band as the shell state. And this band is the core state, which is a typical exciton absorption of our core. And in this table, if we look at the quantum yields in this column, as I prepare the cadmium telluride core, the quantum yield is just only 2%. After I gradually deposit the cadmium selenide shell on it, the biggest one, the quantum yield can goes up to 33%. This is quite a strong evidence. We have removed a lot of surface defect state of the core. And not only the steady state information, we also want to know how do they look like. So we use electron microscope to observe the morphology of this kind of nanoparticles. So as you can see here, they are spherical, they are more dispersed. And here is the size distribution of these nanoparticles. The average size is about 4 nanometer in diameter, and the deviation is roughly 0.2 to 0.3 nanometer, which is just 5%. And under high resolution electron microscope, we can even see the crystalline structure here. And I want to mention one thing is there are actually some of nanoparticles which is commercial available, but we have to synthesize these particles by ourselves. The first reason is it is much expensive compared with the cost of the chemicals we use. It's more than 10 times or even 100 times. And the second reason is more important. In order to get high quality of the spectroscopy result, we need to get a high quality of the particle like this kind of size distribution. And we want to make the particle with the core size as we want. And we also want to change the shell thickness we want for our study. So now we know the steady state information. We also know how they look like. And next we study the PL lifetime by using femtosecond laser spectroscopy. So here we use a femtosecond pulse to excite these particles. And the PL lifetime is measured by using a street camera in our lab. The PL lifetime could be fit by a single exponential decay, like this. So as we can see here, the biggest particle has a PL lifetime about 35 nanoseconds. So in this series of the core shell particles, the core only has a lifetime which is 15 nanoseconds. As we gradually deposit the shell on it, we can see the lifetime just keep gradually increasing. So this result actually demonstrates what I said in the introduction. This kind of material is quite a good candidate for the photovoltaic application. We are able to tune the electron and hole lifetime by chemical method. So we are not only, now we know the lifetime, the PL lifetime increase as the shell coverage increase. So now I change strategy to measure the lifetime. So here I choose the sample 5 as the example. So I choose gallium telluride, gallium cyanide 5 as the example. I change the excitation wavelength. So here are 3 excitation positions, here, here, and here. So I use 3 kinds of excitation wavelength to excite the particle and measure the PL lifetime. And here shows the result of the PL decay. So here are 3 colors, red, green, and blue. So, and I also use a single exponential decay to fit the PL lifetime. So it turns out no matter what excitation you use. So the first excitation wavelength just excite the core. And the second excitation wavelength is actually resonant with the shell state. And the third excitation wavelength is actually pretty high, can excite both core and shell. So no matter which excitation we use, we always see the emission at a constant wavelength with a constant lifetime. So this result indicates the final state we observe is actually the charge transfer state at a constant emission wavelength and a constant emission lifetime. So in this experiment, we know the initial state we created because we are able to tune the excitation wavelength. And we also know the final state from the PL measurement. So we know the initial state and we know the final state and what happening in between. So this figure is actually our suspect. There should be some electron and hole transfer through the interface to get the final state from the initial state. So in order to confirm this point, we use transient absorption spectroscopy to investigate electron and hole transfer and relax. So assuming we have just a 2-level system and we use 2 laser beam to do the spectroscopy. First, I use the laser beam, which is the pump beam, to create some. Okay, so here I use a pump beam to create some excited charge carrier in S1 state. Before the charge carrier relax, I shoot a second beam, which is a probe beam, to take the absorbance. And you will see the reduction of the absorbance because before the charge carrier relax, the excited state is partially occupied. You don't have more room to get the ground state carrier to excite it. So if we monitor the absorbance change at a different time, we are able to make a plot like this, which is the number of charge carrier at the excited state versus time. And this curve, from this curve, we are able to extract how fast the excited state relax. And so this figure shows the typical transient absorption spectra in my core shell nanoparticles. And the strongest one is the core state signal, and the shoulder is the shell state signal. As I excite the core state, I probe the relaxation at the core state. So in this relaxation, I am able to use 5 exponential function to fit it. One component is, the first component is 1 picosecond, and the other component is roughly 19 picosecond. And both components are assigned to be the electron relaxation from the conduction band to the surface defect state. We actually measure the transient absorption spectra of this series of the core shell particles. And here is a tabulated result. So all the nanoparticles, we are able to use the 5 exponential function and got 2 components. the four-state relaxation. The similar strategy I use in PL lifetime measurement. For the transient absorption spectroscopy, I also use different wavelengths to excite. Either excite the core here or excite the shell here. So the left panel shows the core excitation spectra and dynamics, and the right panel shows the shell excitation spectra and dynamics. So what we found here is when we do the core excitation, most of the signal from the transient absorption spectra is due to electron dynamics, and we found the electron transfer rate through the interface is pretty fast. It's actually beyond the time resolution of our femtosecond pulse, and the relaxation rate is about 8 picoseconds. When we excite the shell, most of the signal is actually come from the hole, and we found hole transfer through the interface is also very fast. It's roughly 500 femtoseconds. However, the relaxation rate compared with the electron is actually 100 times much slower. So here I want to use this figure to summarize the charge separation and recombination study in my work. So when we use the laser to excite a core, we create electron and hole pairs. After the electrons are created in the conduction band, the electron has several pathways to relax. Either relax to surface defect state or transfer to the shell through the interface. And from the PL measurement, we are able to measure this charge transfer lifetime is roughly 30 nanoseconds. And when we excite the shell, the hole tends to transfer to the core through the interface, and followed by extremely slow decay to the surface defect state. And I would like to thank all the assistants during this project. I would like to thank my advisor, Dr. Berda, and our collaborator, Professor Gregory Scholes at the University of Toronto. I would also like to thank our department. It's a great opportunity to share some of my experience here, and I greatly appreciate all the assistance from our lab mate in Berla Group. Thank you for your attention. I will be happy to